Thanks for tuning into this presentation. So today I'm going to talk about using static headspace GC VUV to detect methanol in crude oil. As a presentation overview, I'm going to cover four main things. The first one is just to have a brief introduction to our VUV technology. Then I'm going to move into the significance of methanol in crude oil, following some preliminary analysis of methanol in light sweet crude oils, and then lastly, looking at some additional analysis of methanol in various light and heavy crude oils. So let's jump into the technology overview. The vacuum ultraviolet detector, or VUV detector for GC, is an absorbance spectrometer. So it collects absorbance spectra from 125 to 240 nanometers. And what's unique about this absorption region is that mostly everything tends to absorb this type of light. Consequently, it can detect things that are problematic for other detectors like formaldehyde, formic acid, water, carbon dioxide, carbon monoxide, and the detectability on column is from low tens to low hundreds of picograms depending on the compound's absorbance. It also has a linearity across 3 to 4 orders of magnitude and provides both qualitative and quantitative analysis. And the qualitative part is represented by the matching through the absorbance spectra library, and the quantitation comes from using Beer-Lambert's law, where the area of a peak is proportional to the concentration. Or in other words, the absorbance is proportional to the concentration. And we can also separate colluting compounds even when it comes to isomers, and we can do this through spectral filtering as well as spectral deconvolution. So, how exactly does VUV spectroscopy work? Well, when you hook up a GC, the effluent that emerges from the column goes into the VUV detector. And you can see this in the schematic on the right hand or on the left hand side. And when the compounds enter into the VUV flow cell, UV radiation is provided from a deuterium lamp. And as that light is shown on these molecules, the remaining unabsorbed light enters a spectrometer where then a spectral fingerprint can be seen. On the right hand side, I also have a figure of the VGA100, which is a VUV detector. And this detector collects from 125 to 240 nanometers and can acquire upwards to 75 spectra per second. Now, one thing that I do like to clarify is, contrary to the name vacuum ultraviolet, we actually don't use vacuum pumps. And this comes in handy, especially when it comes to method development. When you have to, let's say, change columns, there's really little to no downtime. So, what's the significance of methanol in crude oil? Well, methanol is added to prevent the formation of gas hydrates in crude oils, especially when it's transported, let's say, through a pipeline. Now, gas hydrates, if you look in the image on the lower right-hand corner, is what I like to think of as balls of ice that can catch on fire. So you can imagine if you have methane present in this, let's say, crude oil that's traveling down these pipelines and it interacts with water, it can basically form these solids that can then get lodged on the insides of this pipeline, which would prevent the flow. Now, of course, whenever you add, let's say, compounds to, let's say, the crude oil, eventually you're going to have to take it back out in the refining process. And it turns out that whenever water is removed, since methanol is fairly miscible in water, it can actually go along with the water to these wastewater treatment facilities. And it turns out that if you have, let's say, some bacteria that is used to break down any of this organic material, the methanol can, let's say, distract them, so to speak, where they don't efficiently break down the materials that they're supposed to. So, what exactly can be done to identify methanol in crude oil, or let's say residual methanol in crude oil? Well, it turns out there is a traditional method called ASTM D7059. Now, this method has a variety of configurations, but most of them tend to have analysis times around 20 minutes or so. And in the image on the right-hand side, I just have an example of a chromatogram from one of the configurations where it uses a valve in a backflush mode to basically dispose the heavier compounds, because all of these methods consist of a direct injection of crude oil into your GC system. Now, these methods detect ranges from 15 to 900 ppm of methanol in crude oil with a water content of 0.1% or less. And keep in mind that since this is a direct inject method, you have a risk of just dirtying your GC inlet and also ruining your column. And again, it just requires a backflush technique, which involves timing, switching, as well as just complicating the setup in general. So, at VUV Analytics, we are proposing an alternative method, just really using static headspace GC VUV. Now, static headspace has been around for a while, but instead of, let's say, using an FID detector that most of these ASTM methods use, we're going to use our technology since we can actually identify compounds. Now, this solution is a single column setup, so it's very simple. We don't directly inject like crude oils, so again, we're having the added bonus of not avoiding, so we have the added bonus of not junking up the GC inlet and also just saving our GC column. Now, the majority of these compounds elute in under 20 minutes, and as a reference, methanol elutes in about 3.5 minutes. The image on the right-hand side just shows one of our setups in the lab. We have an Agilent 6890 gas chromatograph, and again, this detector can connect up to a variety of different GCs as well as headspace units. But in our lab, we have the Gerstel MPS2 autosampler, and lastly, of course, our VGA 100. So for this preliminary study, we used an ASTM proficiency testing light sweet crude oil. And we have an image of the canister on the right-hand side. And for those of you that are interested in a visual, I also have a green vial here of what it looks like. Now, light sweet crude oils have low density, viscosity, sulfur, and wax content, and they actually flow at freely at room temperature, and they also have a high proportion of light hydrocarbons fraction in them. So, of course, this proficiency study was, we had to check to make sure there's no methanol, so this was methanol free, and we also used 1-propanol and 2-propanol as internal standards since it's similar to ASTM D7059. So, as a general overview for the conditions used for static headspace GC VUV, the total runtime was 19 minutes with a flow of 1 ml per minute using helium at constant flow. We matched the GC runtime to the incubation period. So we had our incubator at 80 degrees Celsius for 19 minutes, and we had an agitation on as well. And we just used a syringe temperature of 90 degrees Celsius with 250 microliter injection volume. For the VGA 100 conditions, they're fairly straightforward. For the flow cell and transfer line, we kept at 275 degrees Celsius, and we had an acquisition rate of 4 Hertz with an acquisition range of 125 to 240 nanometers. So here, this slide just highlights what the ASTM light sweet crude oil chromatogram looks like. And also for reference, in terms of sample preparation, we used a 20 ml headspace vial with 1 ml of crude oil, and then we spiked in with methanol and the internal standards. In this slide, we have methanol eluting at 3.5 minutes, and this peak is at 1,000 ppm in concentration in the crude oil. And the inset figure is the VV absorption spectrum, and this is a very unique spectral fingerprint of methanol, so it's quite distinct from any of the compounds eluting in this entire chromatogram. Similarly, in this slide, I'm showing where the 2 and 1-propanol elute, where they're at 6 and about 7.5 minutes respectively. And even when we look at their VUV absorption spectrum, keep in mind that they are isomers from one another at 200 ppm in solution. And again, we're quite easily able to distinguish them from one another. So under these methods conditions, we were able to get down to about 5 ppm, and this inset plot just calls out what that 5 ppm peak looks like. So naturally, we did a calibration curve to test the linearity of things, and we went down from 5 ppm all the way up to 1000 ppm in triplicate, and we obtained an R² of 0.996, indicating that it is indeed a linear fit. So these next few slides are just going to highlight some of the RSD percents for replicates. And this first one is the 5 ppm methanol, our lowest calibration curve. And to give everyone an idea, this is has a signal-to-noise ratio of about 4. And again, this is sort of approaching our method detection limits here. But again, 7 replicates at 3%, which is pretty good for headspace analysis. Moving on to ASTM's lower limit of 15 ppm, we see an RSD percent of 3.4% for 7 replicates. And then for a higher concentration at 750 ppm, for 7 replicates, we're getting RSD percents around 2.2%. So I went ahead and did a short-term methanol's repeatability study for static headspace GC VUV. And several replicates were taken over 3 levels over 3 days, totaling 21 replicates for each level. So the main takeaway from this slide is that the RSD percents across the board is less than 9%, which is pretty good for headspace analysis, since RSD percents tend to be a little bit higher than, let's say, direct liquid injection. So the previous slides really just looked at examining methanol in this ASTM proficiency light sweet crude, and naturally the next thing to say is to look for is to see if this methanol would be interfering with any compounds that are also light sweet crudes, and just to see if there's a matrix effect. So in this case, we looked at 2 additional light crudes that were free of methanol. One came from Colorado and the other one from Louisiana. And they were spiked with 100 ppm of methanol, and GC headspace VUV analysis was performed on them. So this slide just highlights the ASTM proficiency crude in black on the bottom, the Colorado light sweet crude in orange, and the Louisiana crude in blue. And overall, they tend to have similar profiles in the sense that they have a lot of information in the lighter end, in the front end, the chromatogram. So just to kind of call out some compounds, we have oxygen, which is going to be present in the headspace itself. These compounds, these crudes had pentane, benzene, toluene, xylene. And you'll see the presence of cyclohexanone, which was used to dilute methanol to the desired concentration, to the desired calibration limits. So conveniently enough, in each of these light sweet crudes, no peaks interfered with methanol, so we got lucky there. And on top of that, the areas seemed to be somewhat similar, so there weren't any significant differences, suggesting that there doesn't seem to be a matrix effect. So, of course, the next thing to do then is just to examine some heavier crude oils with static headspace GC VUV. Now, heavier crude oils tend to have higher viscosities, densities, and larger proportions of higher molecular weight. In other words, there's not going to be as much volatile compound, so we would expect the front end of the chromatogram to be less exciting, so to speak. And several heavy crudes free of methanol were spiked, again, with 100 ppm of methanol and analyzed. And to give people a visual of what these heavier sweet crudes are, in my mind I kind of think of this very black tarry substance which you might see in this beaker, but actually it's just a lot darker version of that lighter sweet crude that we've seen. It's still free flowing at room temperature, but it's just a little bit more viscous. And in general, these crudes that we analyzed were from, let's say, South America and the Middle East. So as a chromatographic comparison for the headspace analysis, on the top in blue we have the ASTM light sweet crude compared to this Azerbaijan heavy crude on the bottom. And right away you can see that the intensities across the board is much less in the heavy crudes versus the light crudes. And also the density in the front end of the chromatogram is much less in the heavier crudes than the lighter sweet crude. So this slide just highlights again the samples that the heavy crudes that we compare to the ASTM light sweet crude. And just to call out some compounds for reference, again we see oxygen in the beginning. Surprisingly, these heavier crudes had large amounts of acetone, but then we see other compounds like hexene, benzene, toluene, xylene, and again near the tail end we see the cyclohexanone that was used to dilute methanol. So if we went ahead and checked the methanol region around 3.5 minutes, it turns out, hey, there's no coelutions. But among that, we also see that the areas are pretty similar. So there's no significant differences from this light sweet crude for this 100 ppm methanol versus these heavier crudes. So in summary, using static headspace GC VUV for methanol detection in crude oil seems to be a possible good alternative. In this presentation, we demonstrated that the linearity ranges from 5 to 1,000 ppm with acceptable RSD percents, much less than 9%. And there doesn't seem to be a quantitative bias or towards heavy or light sweet crudes between the two. On top of that, just using static headspace alone is a lot cleaner than doing direct injection because you don't have a risk of ruining your GC line or a column, as well as just simplifying the setup in general. Now, those of you may be thinking out there, hey, what if you just used FID instead of VUV? Well, sure, that could be done, but I would really like to highlight an important feature is that VUV can easily discern a lot of these different peaks in the headspace chromatogram besides just the methanol. So if, let's say, there was a coelution, we have a much better chance of deconvolving that type of risk versus an FID detector. So I would like to thank everyone for tuning in, and I hope you enjoy my presentations in the future.